Hello everyone, welcome to my Programming 1 class. The previous times I taught this course online, I used old lecture videos, but I went ahead and re-recorded all my videos and I edited them. I made a lot of cuts so that the videos aren't as long as they used to be, and I'm hoping this makes it easier for students to take this course online. This is a difficult class and there is a lot of information to go over, so it's up to you to make sure you're keeping up with the videos and doing the quizzes and the homework. We're going to start in Chapter 1. Chapter 1 can be divided into two parts. The first part is on computers. If you're a computer science major, you will have to take a computer architecture class and go into a lot of details about computers. But this is an entry-level programming class, so I don't want to focus too much on this section. The second part of Chapter 1 is an intro to Java, and from that point on, anything that you watch in the lecture videos or anything that you see in your homework or your quizzes may appear on your exam. So let's begin. So one of the basic concepts obviously is hardware and software. It's important to know the difference between the two. Hardware are the things that you can touch, the tangible things on your computer, anywhere from the monitors, the keyboards, and the different components within the case of your computer, like the CPU, the motherboard, the RAM. Software is essentially just the data and the programs that are on your computer. Here's a drawing of the CPU. It's kind of important to understand how this works. So the CPU is actually the brain of your computer. It's receiving instructions and it's going to use those instructions to determine what to do within your computer. It actually runs in the cycle of fetch, decode, and execute. And it's reading in these instructions, it's storing things in its registers, it's storing things into memory, and it's making your computer actually run programs. Your computer has input-output devices, there's secondary memory devices. Now here's an important topic, is the different software categories. It's important to know what an operating system is. The operating system is actually the most important software. It's actually the interface between the user and the hardware. It's what makes the hardware usable. So it provides that interface. So some examples of some operating systems. For Windows, we have Windows 10. For Mac, you have whatever the latest version of the operating system is for Mac. You have Linux and Unix. There's also operating systems on your phone. So if you have an iPhone, then you have the iOS operating system. If you have an Android, you have the Android OS. An operating system is needed for any hardware that has some type of software interface. Application programs are just a generic term for other types of software that we have on our operating system, like word processing or video editing apps or anything like that. Analog versus digital. So everything on a computer is digitized. So the best example I can give of this, and the example they give here is over a record album where the information from a record is actually the voltage with coming from the speakers. It's like directly proportional. I think that's maybe like an old example. The best example that I can give you is when you see things with your eyes. I can look out my window and I can see things. You can take a picture with the highest quality of the same thing that you're seeing. And when you get that picture, it looks really clear. But as you zoom in to get more details, you start to notice that things start to look pixelated. Now, if I'm looking at things with my own eyes and I were to zoom in, meaning like I were to get binoculars or a telescope, I could keep going deeper and deeper into what I'm looking at, and I can get a clear image of what I'm looking at depending on like what I'm using to see further away. So that signal from my eyes to my brain is an analog signal, meaning there's lots of information there. It's just my mind isn't able to process it all without the help of, binoculars or a telescope. But what I'm seeing is actually a lot of information. And the way the computer works is the computer has to digitize all that information, meaning it takes samples of that picture that I'm looking at in order to store it within a hard drive or just store it within the computer, because it's impossible for a computer to store all that information. Otherwise, it's going to eat away all the hard drive. It has to be digitized, meaning it's sampled. Like at certain pixels, it's sampling and saying this pixel is this color, this pixel is this color. It has to do that in order to store that information within that computer. So here they're talking about like how things are digitized, where you have your signal and it's just sampling at different spots within that signal. And even like when we represent text, all the characters from the English language, we break them down into numbers, and then those numbers can be represented into binary numbers. And if you look in the back of your book, or if you don't have the book, if you just go online, look up the ASCII character set. That's how we represent digitized character data. Now, Java does use the Unicode character set, which is more expanded than the ASCII character set, where you can have international characters, but we'll talk about more about that when we get into chapter 2. So the way binary numbers work is a computer communicates through electrical signal. So either that line of communication is not charged or it is charged. Essentially, you have either a 0 for not charged or a 1 for charged, and that's how information is able to be digitized. So depending on the lines of communication, so for instance, if I had 2 lines of communication between me and somebody else, and the only way that we communicated with each other is either I charged a line or I didn't charge a line, if that was the case, then for each line, there's 2 possible values, either a 0 or a 1. So that specific example would be if I had 2 bits, 2 lines, and these are all the possible permutations. So with 2 lines, I can represent 4 numbers. If I had 4 lines of communication, 4 bits, then I can represent 16 possible permutations. Each permutation can represent a particular item. There are 2 to the n permutations of n bits. Therefore, n bits are needed to represent 2 to the n unique items. So here's an example. So basically what they're saying is, since we're digitizing everything, we need a specific number of bits, like 2 to some number of bits. So if we wanted to represent all 50 states, how many bits do we need? Now, 2 to the 5th power is 32. So 2 to the 6th power should be 64. Yes, that's correct. So if we had 5 bits, we could only represent 32 items. But if we had 6 bits, we could represent 64 items. Since we have 50 states, if we wanted to digitize the states, we have to use 6 bits so that we can get all 50 fitted into the number of bits that we have. So we would need 6 bits so that we can represent 64 different permutations, and that's big enough to fit into 50. But when we use 5, we only had 32.